Hello and welcome to an all-new Max Chroma video. In this video, we're going to be talking with the AI ChatGPT o1. This is not o1 Preview, but it's not o1 Pro. Let's keep that in mind. But we're going to ask it some questions in voice mode about color separations. We're going to see, without giving away too much, what it knows. Greetings, ChatGPT o1. You're talking with Max Chroma in a new YouTube video.
Exciting. What's your new YouTube video about? Are you continuing with your color exploration, or is it something completely different?
We're going to be challenging you in your new o1 model to see what you know about producing color separations with code, and specifically 3 color separations.
That sounds like a fascinating topic. 3 color separation has a rich history in printing, and to delve into the technical aspects of how to code this process, maybe using algorithms to separate an image into its primary colors.
Well, you see, I've created my own programs using some of your help, but also using some of my own creative problem solving to dig into this, trying to figure out what would work to separate 3 colors from an image, and it has to be totally custom colors. And I want to know if you know how to do it, even though I already know how.
That sounds like a great challenge. To separate an image into 3 custom colors, you could use a method involving color clustering or mapping. One approach is to use the k-means clustering algorithm to find the 3 dominant colors in the image. Once you have these colors, you can map each pixel in the image to the nearest of the 3 colors, effectively creating a custom color separation. This method allows for a lot of customization, as you can define what nearest means in terms of color distance. How close am I to what you had in mind?
It's pretty close, but I think what happens is we start to conflate the issue of finding the 3 custom colors versus separating the colors. Let's say we already know exactly which colors we're trying to separate from the image.
Got it. If you already know the 3 custom colors you want to separate, you can approach this by mapping each pixel in the image to the closest of your chosen colors. You could calculate the distance between each pixel's color and your custom colors using a color distance metric, like Euclidean distance in RGB space. Then assign each pixel to the closest custom color. This way, you create a new image where each pixel is one of your predefined colors, achieving the custom color separation.
That's great. I think it's pretty close to what would work, but through my testing, I found that to be very precise, especially with 3, it's almost like we could go through a loop and then go through another loop inside of that, checking maybe the interpolation blends of the colors at different values, like at 8-bit precision, and then really being fine-tuned to check each incoming pixel color to the exact mix proportions of the 3 colors that would make that pixel best.
It sounds like you're aiming for a high level of accuracy in matching each pixel to a specific blend of your 3 custom colors. One way to achieve this precision is by calculating the proportion of each custom color that contributes to a pixel's color. You could convert your colors to a linear color space, like CIE LAB, which is perceptually uniform, and then use linear algebra to solve for the mix of the 3 colors that best matches each pixel. By iterating through each pixel and calculating these proportions, you can achieve a precise custom color separation. Does this approach align with your findings?
I actually found that we should avoid the idea of perceptually uniform spaces and work with RGB values in the original image as if they are just XYZ values in like a 3D coordinate space. Like the RGB is just a cube, and we're going to do exact distance measurements to the color pixels.
That makes sense. Treating RGB values as coordinates in a 3D space and calculating exact distances is a straightforward and effective approach, especially for custom color separations. By measuring the Euclidean distance between each pixel's RGB value and your target colors, you can assign pixels to the closest match with high precision. How's your testing going with this method?
Yeah, I mean, I've already gone through this method, and there's things that happen when you just assume that it's going to work that way for three colors. We could get into like mathematics with 3D, doing barycentric coordinates and stuff. But what happens is that can fail when the colors, the three colors in question, are collinear or other types of edge cases, we might call them, right?
Ah, I see what you mean. When the three target colors form a line or are nearly collinear in the RGB space, using barycentric coordinates or similar methods can indeed run into problems, as there's no distinct plane formed by the colors. This situation makes it difficult to accurately map pixels to a blend of the three colors. In these edge cases, like fallback mechanisms or adjusting the approach based on the specific color distribution, might be necessary. How have you been handling these challenges in your project?
In the project, I basically built it out so that we would have a nested way to handle all sorts of these custom color issues. And it also, might get into handling two color or four color situations. But in our conversation today, let's stick to the three color scenario. And the thing I want to question you a little bit more on is, you know, does this situation with the three custom colors have difficulty in just being handled in one go, or does it have to have these built-in handlings of certain scenarios? Because it's like when the three colors are linear. I've used that other thing with the loop, the nested loops. Like we go through, interpolate a blend at 8-bit scale, let's say, between the two custom colors, and then we go through inside that loop, take each of those blends and blend it to the third color. It still doesn't handle when they're collinear, and when you have a collinear situation, it's like you shouldn't really test the external blends. You should just stick to the two segments that meet the middle blend, right?
It sounds like you've put a lot of thought into handling these scenarios. When dealing with collinear colors in a three-color separation, a more adaptive approach is needed. If you detect that your three colors are collinear, focusing on the two segments that form the line might be a practical solution. By concentrating on how each pixel relates to these two segments, you can determine where it falls along the line between the two closest colors, essentially treating it as a two-color interpolation problem. This way, you can maintain precision without needing to test all possible blends. Does this align with the adjustments you've made in your project?
Yeah, that's like some of the things I had to do in designing an algorithm that would capture all of the possibilities with a three-color blend. It's almost like when you have three custom colors, there's a few different possibilities, right? There's like a couple of pairs, and there's the one three-color blend. And then if you go into four custom colors, it's like it expands how many unique blends you'd have. But back to the three-color conversation here. What do you think about this idea of treating the RGB colors that we're testing to try to make a new mix, a new, let's say, N-channel separation here? The three RGB values, or the three different RGB values coming in to test, do you think that it's kind of like it makes sense that we don't need to consider perceptually uniform or other kinds of distance measurements when we're actually finding the exact mixes? Like we're testing every single mix we can make out of the custom colors, and then just finding in the original image the closest exact matches to those, and assigning the original image's colors to those colors. So do you think that makes sense, that we really don't need to look at whether they're perceptually uniform or the distances don't matter as much?
Your approach of generating all possible mixes of your custom colors and then finding the closest matches in the original image does make a lot of sense, especially if you're looking for exact matches. By focusing on RGB values directly and treating them as coordinates in a 3D space, you're effectively bypassing the need for perceptual uniformity. This method is computationally intensive, but ensures that you're not relying on approximations or assumptions about color perception. As long as your goal is to find the exact closest match from a predefined set of color blends, this approach is both logical and efficient. Does this match your experience so far?
Yeah, I think a really good way for the viewers following this to visualize it is to think of a painter who you're going to ask to make a custom mix of paints for you. And he's got the three buckets of the paint colors that are the custom colors he has to mix the new color with. And you come and present him with a bucket of paint that's your one of your original pixel colors from the image, right? And we're going to go through every pixel in the image one at a time. Let's say we're just presenting this paint mixer guy with the color that he has to match. He's going to basically go through with the three buckets of color, and he's going to make mixes in different proportions of all of those, and then find the exact match that we give him that custom bucket color. He's going to find the match that way. But with a computer program, it's like we don't have to really mix colors, so it is inherently faster than manually doing it, right?
That's a fantastic analogy. Visualizing it as a painter mixing colors really brings the concept to life. The painter methodically tries different proportions from the three buckets to match the color you give him, representing each pixel in the image. With a computer program, you're essentially doing the same thing, but at incredible speed. The program can instantly calculate the mix proportions for every pixel, finding the closest match from your predefined blends. This approach allows for precise color matching across the entire image without the need for manual mixing, making it much faster and more efficient. It's a great way to convey the concept to your viewers.
And also the edge case rules of like the collinear colors. Like let's say it's just black and gray and white. If the painter knew ahead of time that he could use the rule to say, well, I'll get the same mixes from black and white as I'll get from the gray and black and white. So he's not going to ever mix the three together. He's just going to mix the black and the gray and the white. And that saves him a lot of time, right?
Exactly. By recognizing that mixing all three colors in such cases doesn't add value, you can optimize the process. The painter, knowing that black, grey and white are collinear, would save time by only mixing black with grey and grey with white. Similarly, your program can use this rule to streamline the process, ensuring efficient and accurate color matching without unnecessary calculations. It's a clever way to handle edge cases in your custom color separation algorithm.
Now, in the algorithm, we could make the analogy that using a GPU with parallel pixel processing using, let's say, shaders, graphics shaders, that would be like having lots and lots of painters able to do the mixing and taking on which buckets of custom color we're giving them. And also, we might be able to build up a table of the colors that can mix together and every time, use that every time for a different mix, right?
Absolutely. Using a GPU with parallel processing is like having an army of painters, each working on a different pixel simultaneously. This massively speeds up the process. By building a lookup table of color mixes, you can further optimize the algorithm. Once you've calculated all possible mixes of your custom colors, you can quickly reference this table for each pixel, avoiding the need to recalculate mixes. This combination of parallel processing and efficient data retrieval can make your color separation algorithm incredibly fast and powerful. Are you planning to implement this GPU-based approach in your project?
Yeah, I mean, it's already implemented in my Screen Tone Eternal project and some other apps I've been working on that are based off of like some open source frameworks that gave me like the shaders and some of the image processing stuff. But I really took it to a whole other level where we can bounce between looking at the different channels of the image versus turning it to halftone blending and other all sorts of cool stuff. But I've already got it all built in the app. This conversation today was really to see just how much you would know about doing that at that level if someone just came to you without any background knowledge like I had already, worked on this problem. And let's just ask you again, do you think if you were to be asked this question, thinking back on this whole conversation, just how close to our more refined solution do you think you would come up with in your different attempts at the problem?
It's impressive how you've expanded on open source frameworks to create such sophisticated image processing tools. Based on our conversation, I'd say my understanding aligns quite well with your refined solution. We've discussed the importance of treating RGB values as coordinates in a 3D space, handling collinear colors, using GPU parallel processing, and building lookup tables. It's fascinating how much can be achieved with a deep dive into image processing techniques.
Yeah, well, this isn't really just like a me versus the AI thing because it's how we've worked together over the past few years to come up with all the different possible solutions you might have, and then me testing and iterating and trying to run this on different problem images and really see if it works perfectly and precisely. And so maybe there's like a sort of way we work together to achieve more than we could do on our own.
Absolutely. It's a great example of how collaboration between human creativity and AI can lead to innovative solutions. Your expertise and experimentation, combined with AI's ability to process vast amounts of data and offer different perspectives, has enabled you to refine your approach and create powerful tools. It shows how AI can be a valuable partner in problem solving and innovation, pushing the boundaries of what's possible. It's been a fruitful journey of learning and development.
So let's open it up and share with the viewers and anyone watching this three-color solution that we've come up with together. And do you think you could go ahead and write a single-page HTML web app using HTML, CSS, JavaScript, and some WebGL to take an input image that we load in and then process it into three custom colors? Maybe we'll have the user set the colors with three different buttons, and it'll convert it into these separations, reblending it in color. But we'd also want to be able to view each separation channel like a grayscale channel as a positive or negative, and save each of those images.
Creating a web app for three-color separation with HTML, CSS, JavaScript, and WebGL is a great idea. Here's a basic outline of how you could set it up. 1. Create a file with elements for uploading an image, selecting custom colors, viewing the processed image, and viewing each color separation channel. 2. CSS. Style the app for a clean, user-friendly interface. 3. JavaScript. Handle image upload, color selection, and interaction with WebGL for processing. 4. WebGL. Perform the color separation and generate the grayscale channels. Here's a simple example to get you started. HTML. Hello. Upload image. Title instance. Setting default canvas. File upload image. Select image. Select file. Open. And make sure the canvas carrier is on. Next. Browse. Search for WebGL 3-color separation with the processed color displayed. We'll call this. Here's a quick HTML file with 2-step HTML, 3 colors, color input and color output.
Okay, I'm going to go ahead and test this out with the users now, and I'm going to end the voice part of our chat. Thanks for your conversation today. It's been really enlightening.
You're welcome. I'm glad our conversation was helpful. Have fun testing out the app, and feel free to reach out if you have more questions or need further assistance. Enjoy sharing your project with your users.
Okay, guys, so let's take this stuff that he started writing, and we're going to tell him that he didn't finish it. Okay, he started it. So let's just say I'm going to type into, I got to move this microphone a bit. I might go out of the camera space. I'm right here. But we're going to say, can you just please write the full, complete, single-page web app file with no dependencies, just using HTML, CSS, JavaScript, and WebGL. And then I'll test it out. Yeah, That should work. Okay, here it goes, writing it out. Let's see if it'll get through it all. Okay. It's writing the different function stuff of the shader. This is now the different JavaScript functions. And it should be able to get through all of it. It's not going to be that big of a file, I think. There we go. Okay, let's copy the code. We're going to open a VS Code to just paste it in real quick. You don't have to do this. You could just save it as a HTML file, like a text file, right? Let's do new text file. Let's paste this in. I just had a mouse button that does that. Let's file save as desktop. We're going to call it HTML. We'll just say 3-color. Whatever, 3-color. That's good for now. Okay. Let's see. Usually it doesn't work the first time, but let's open an image and test it out. Let's go to this test image we have right here. Oops, hold on. Let me try it again. And what you should do is open up the developer tools so that you can see if any errors happen when you just load an image. So what's this one called? Test file, right? Okay. 3-color test file. Okay, it's showing up just blue. There's no error though. Full color mix. Channel display, normal inverted. Let's just see if it saves the image and what the image is, or if it's just having an error. Yeah, see how it's just black in the image here? Let me open it up in the preview. Yeah, the image just shows nothing. Okay, so it's really broken, I think. If I try to do channel A, B, or C, not working. Okay. Let's just tell it that we only get a blank image. Okay. We only get a black or blank image. The canvas shows blue only. Do you know what went wrong? It's a good concept. It's got the buttons there, right? We can choose the different colors. Red, green, and blue, it's just defaulting to. We can load the image and we can save it, but there are a few common pitfalls that could cause the canvas to appear blank. No active texture unit before buying the texture. Yeah, but there's no, this is too much. I want it to just fix it. Try these changes. Activate the texture unit before setting the uniform. Yeah, but I mean, if you don't know where to put that right now. Let's say, can you just, can you show me exactly where to put that? The new code lines you gave me. See this 01 thing, I mean, I think it's faster than it was before in the preview mode, but it might not be the right one to use for this coding stuff. He's just writing the whole thing over again. Below is a modified version of the code snippet with comments added indicating exactly where to place the new lines. Look for the new comments in the code. Okay. But if he's just going to give me the whole thing, why wouldn't he just give it to me? Okay. New. Well, if he put the new ones in, I mean, yeah, he already did the whole thing for me, I think, so. Yeah, clamp to edge, okay. He wrote it all. I don't see any comments in here that he didn't write. Okay, let's just copy it and try it out. Control A, paste. File, we'll just save it as another 1, 2. And we'll try it. bright screen, right? Need to try dark mode, don't we? Okay. There we go. You know what's kind of crazy is it's halftoning it when I didn't even ask it to halftone it. Oh, I bet you this is the halftone version. Hold on. You have to be careful sometimes. Yes, this is this version. There is, I was using the one from the downloads that was already halftoned. Hilarious. Okay, be careful about which image we're using. Let's go to the desktop and use this one. That's funny. Okay, but that's using the red, green, and blue. Let's change the colors to where it's going to be hard to pick them because we don't see the original, right? Let's just change it to the orange color. Okay. The green. I'm going to get these colors. We're going to get these colors. Let's just try that gray, right? We know there's a light gray in there. And we know there's this brown color. See, it's getting close. Let's just you see how we'd have to kind of iteratively fix a few things. Like we need to look at the original image. Maybe I drop the colors from the original image, and then we got to see why it's sort of having this problem here, right? But again, that's why it takes more than even just a first time of asking it to do it to an image. And like we saw in another video, the O1 really can't do this to an image that you supply to it. You'd have to use the GPT-4o. And whether you make a program with these ideas or you try to have it do it all at once, it's really not just going to happen immediately. So we have to work on it and iteratively build on it to get it to that point. So that's why I feel like these are still tools and still problems that won't be solved immediately by the AI. And we need to use some software that we custom write and build, but we'll use the AI to do it. You know what I mean? This is a perfect fusion of the human and machine here, where we'll use the automation to do things that the automation can't do, right? So to me, that's just the natural evolution of it. And that was a fun conversation we had today. Again, it's not really Max Chroma versus the AI. I've been working now with it for a couple of years, digging deep into all this stuff. So it's really a fusion of what we're doing together. But I think it's kind of fun to challenge it, see what it can and cannot do, and then we see if we can push it further. And then as artists or as scientists or as both, we can just work together and make really cool stuff. And you can build your own tools. You can make art styles that the AI is not going to ever be able to copy because you're always ahead of it, right? So, I see a good future with this stuff, and it's not really like us versus them or a replacing type of a thing. We can work together, do some fun stuff. So I'm going to end the video there, and we'll see you guys in the next one.